evening. I'm Lorenzo David, and today I'm going to talk about container security with Falco. I'm a senior software engineer at Sysdig, a company based in San Francisco that is essentially providing a monitoring and security solution for infrastructure. And today's talk is about a security tool that we developed internally at Sysdig. It's a completely open source tool that we donated to the CNCF Foundation. Essentially today I'm going to cover 3 points, and I'm going to hopefully be in the order of the 30 minutes, half an hour in terms of time. And I hope I can get as many questions as possible, so to kind of drive the conversation where you have more interest or in the areas that are not maybe clear. As I'm going to try to pack a lot of information here, and I'll try to be kind of very precise in covering the essentials. What am I going to talk about? I'm going to talk about essentially the security problems that Falco solves as a security tool, based on that, we're going to understand what is the architecture and its design, and we're going to see how Falco can be used in action in your infrastructure or as a building block for your projects. So Falco is essentially a security tool, and as security is a very broad topic and it means a lot of things to a lot of people, it's important to define what is the scope of the tool. We are in infrastructure, in the infrastructure space, of course, and in the infrastructure there's a lot of activities, some of which are clearly can be clearly marked as good or positive, and therefore can be clearly decided, and we can clearly decide to allow them in the infrastructure, and other that are clearly non-authorized. For instance, accessing to an endpoint with the wrong credential is something that we can stop immediately. But there are other activities which are not that clearly markable, and we can kind of call them suspicious, in the sense that there are activities that per se they cannot be blocked just based on what we see in the moment that they arise. But we might want to kind of send some information, some alert, and provide more context to that event, to that activity, so that someone can clearly understand what was all the things around that activity that led to that suspicious point in time, and kind of decide whether it's something that we want to allow or not allow. But to do that, essentially, we are mainly focusing with Falco on those suspicious activity where we are not actually doing any sort of prevention. We're not stopping them from happening. We're mostly interested in detecting them. We want to detect that something suspicious happens, but we let it go. We don't. We just inform some operator so that they can take some further action in terms of further analysis, essentially. And in particular, Falco and today's talk, and in general, the open source project is mainly focusing on detection at runtime and forensic, and in the forensic space, in the sense that we look at here and now, in terms of runtime, and then we look at the forensic, which means the past. So we can kind of focus our attention into this space, while the forecast part, which can be clearly stated as I look at what was the past and the present and try to kind of forecast what is the future, and somehow either profile or baseline my infrastructure. That is something that is not currently part of the open source project Falco, but we can clearly see Falco as being a building block for that side. So now that we know what is the goal of Falco, what is actually Falco? Falco is essentially a runtime behavioral activity monitor for container native infrastructure. in particular, as I said before, it's a CNCF incubated project. We are in the sandbox state. And we're mainly integrated with the classic Docker and Kubernetes, which are the container runtime and container orchestrator of main relevance. But as you're going to see from the architecture and the main design principles, we support actually a lot of other container runtimes and orchestrator like Mesos or Swarm or OpenShift. And this is all due to the architecture that we've put in place. What are we actually talking about when we talk about Falco? We are essentially talking about a program that lives on a host, whether it's a VM or a physical server, and that we can easily install it as a classic Linux program with apt-get, rpm, install, and so on. And clearly we can also run it as in the form factor of a container. I've been kind of putting here and there into the presentation some links so that if you guys want to kind of get hands-on to Falco, hopefully by following the presentation and the video that has been recorded, you might want to jump to each and kind of drill down into each individual slide and see how to actually install it on your machine or in your particular environment. There's a lot of documentation and there's a lot of various flavor of how to do these things. So I kind of let the single person to kind of look into that. But essentially, as to kind of wrap this slide, we're talking about the user space process with some additional components that you can easily install it. And in a nutshell, what do Falco do in terms of very practically? And I'm going to try to kind of explain this slide, which I'll be jumping immediately into a demo. But essentially, we see Falco on the top and the user typing commands on the bottom. And I'll try to kind of if I'm able to escape from the presentation and do this, to kind of do what I'm showing here in the demo. So we can run Falco on the top half of the terminal, and as you can see, it requires root privilege to be launched. And the moment it's launched, it gets by default some files that are placed in that we ship by default and that are placed in very particular location, well-known location. And these files contains a bunch of rules that we can look and essentially they describe in a descriptive way some sort of domain-specific language that Falco uses to enforce the detection that I showed before. So in order, for instance, to catch that someone is doing is spawning a shell into a container, we can write a rule that looks like this with a particular condition that refers to macros like spawn process, container, and so on that can be defined below the actual rule, and can output something that looks like a very readable output. So we, as I said before, we ship these main activities that we believe and that are generally believed to be some sort of suspicious activity. So they're not necessarily bad per se. So it's very hard to stop them because an operator, for instance, is totally it's totally normal that it jumps into a container, maybe for troubleshooting, spawning a shell. But it's also something that we want to be alerted on. So without the entire context, it's hard to stop this, or it might make sense or not to stop or to take further action, essentially. So that being said, we have Falco running on the top, and if we do something like we run, for instance, a busy box where we, with this classic syntax, we actually have a shell into the container, we see that a line gets printed right away, which means that, and this is the runtime detection, it's the moment the event happens, Falco detects it and outputs it. And as we can see, we have all the information related to, for instance, the user, which is root, and all the possible metadata that has been printed with the output. And if we do other things, like, for instance, if we touch the classic pipo file under root, we see that that's also something that we actually inform the person that is looking at this terminal that activity happened. And this is kind of just to give you a flavor of what Falco does. The rule itself, as I said before, we ship it by default, but you can write it yourself. The language is fairly explanatory. And as we're going to see in the next slides, it's very easy to extend the rule set and to customize it for your use case. So that being said, let's try to kind of see what is to go to the second section of my talk, which is the part where I explain what is the architecture and how we came out to build and to define Falco with all its capabilities. And we need to take a step back and talk about sysdig. And essentially, the architecture that we relied on and the components that we relied on is sysdig, which is another open source project of sysdig itself. So, and that we release also to the CNCF. So actually, by understanding Falco, we actually we need to understand also sysdig, which is an underlying component that is, you can kind of look at it as drawn into the Falco as a process, as a Unix process. So sysdig is mainly a monitoring tool. It's not a security tool. It's mainly used for very different use cases, from performance monitoring to performance troubleshooting, or to just gain visibility to what an individual process is doing, or the entire machine. And let's kind of see how sysdig does it, and essentially how also Falco does it. So if we look at a single host machine, so right now we're focusing our attention onto a virtual machine or a physical host. We have the classic division between, from an OS perspective, from user space on the top and the kernel to the bottom. And the user space talks to the kernel using a POSIX interface. Every time a process, whether it's within a container or a classic Unix process, needs to send a message over the network, or open a file, or write to a file, he needs to perform a various steps of operations that requires himself to talk to the kernel with the classic interface. And that interface essentially is what we refer to as system calls. And the main idea behind the sysdig is that by some sort of instrumentation of the kernel, and essentially with a complete transparent approach with respect to the application, no matter whether we're talking about container or application running on a JVM or process or bare processes in user space, we're able to intercept every single system call with this module using some trace points, essentially. And this is where the interception happens in the kernel with the very low latency. And then this gets propagated up to the user space process sysdig to essentially a collector. And that's where all the heavy lifting on the logic, on the grammar, on the matching, on the filtering, it happens. So that we can, for instance, say that we're only interested into the system calls that the container Nginx is actually doing. So we can filter out all the system calls to a particular container into the logic that is in the user space part. And very recently, we've announced another kind of support to SysDig with ebpf. So the only change, the only difference between this slide and the other is that the layer on which we intercept the system calls changed, and there are some major advantages that you might be interested on, and maybe we can cover it later. Essentially, ebpf doesn't require you to load the custom kernel module from SysDig, and it runs in essentially a virtual machine, an in-kernel virtual machine that is programmable through user space. So you can think about it as SysDig being a client of ebpf, injecting code into the kernel that is safe and verified by the kernel infrastructure, the Linux kernel infrastructure. And so you essentially don't need anymore to load a dedicated kernel module for SysDig. But if you're not particularly caring about the low-level details, all the things that are in user space and SysDig doesn't change. It's just purely a kernel detail at this point. So let's try to see also what we do. And with SysDig, we don't just trap system calls. We're actually we're also able to gain visibility into other kind of metrics like statsd, which is a well-known protocol. So SysDig embeds a statsd server, so it understands the statsd protocol, so that application can write custom metrics and ship it to SysDig, as well as JMX metrics. So for those of you who are familiar with Java, we're also essentially querying the classic JMX metrics from the JVM. This is just to give you an idea. There's a lot of other kind of things we can collect. This is just to give you an idea that we're not just coming from the bottom up from the kernel, but also horizontally as a kind of interceptor or a kind of daemon of this kind of metrics protocol. Now back to Falcos to kind of once we kind of get the idea of the bottom part, which is the intercepting piece of the infrastructure, and then the collector and the filtering, there is another layer that we added, and that's where the main logic of Falco and the main contribution to Falco is in terms of security. So it is possible not only to filter out system calls as with SysDig. With Falco, it's right now possible to express with some sort of syntax a set of conditions on which we can match. So this is the rule set that I showed before. So at this point, it's kind of clear that the detection workflow works, for instance, to kind of explain the demo that I showed before, works from the bottom up. We trap the system call clone, the exec, and all the things that happens on the bottom. We recompose it. We have some sort of notion of the state of the infrastructure. We know that that clone comes from that container. We can resolve the container name, and there is a whole kind of state machine internally in Falco, because as you probably know, the amount of system calls that are done from a library call or from a user space application is very big. So and they don't necessarily have all the context. So we actually help to we actually have all this logic that kind of makes the user eventually to write very simple rules with the macros and for instance referring to the container by container name or things that are very handy from a user perspective in terms of writing these kind of rules. And then we alert. In the example I showed to a file to the terminal, but we can output to a file and essentially to other kind of mechanism. But this is kind of like the overall architecture. So this is again just to kind of refresh what does a rule look like. And as we can see, there is essentially the matching condition, and there's all the things around in terms of what is the output, the tag. We have a notion of a tag and so on. And of course, this kind of output can be fairly easily integrated with the CNCF ecosystem or other open source tool that can kind of grab all this kind of log and make some sense out of it. But this is just to kind of give you the essential building block of the rule set. Now we're at the point of the talk where I'll try to kind of show how Falco can be actually used now that we know what are we looking for in terms of a security tool, what is the architecture. Now let's look at some use cases that are maybe more interesting and more real life. And of course, classic container orchestrator of the moment is Kubernetes. So let's look at this case, but whatever I say can be applied to OpenShift or Mesos or other container orchestrator. We're not, as you've seen from the infrastructure, from the architecture, we're not particularly tied to Kubernetes. As we instrument the host, we don't instrument the container, or we don't actually instrument the pod or other components that are tied to a container orchestrator. So we move from, in this picture, we're moving from the single host. So before we were focusing on host number 1, for instance. Now we're looking at a 3-node, 3-host cluster, or you can think about it as a multi-host cluster, where we have a bunch of services running with different colors, classic Kubernetes kind of scenario. We deploy Falco using a Daemonset. There you see the link to how to actually do it yourself. It's very simple. It's a classic Kubernetes YAML, and you can deploy Falco as a Daemonset, which means 1 per host. At this point, Falco is instrumenting the host, so all the activity on that host in terms of container, programs, and essentially the system calls of that host are all instrumented. And Falco requires to be a privileged pod to do so. And essentially from there we can kind of look at more advanced use cases where Falco does not only provides you the possibility to filter by container, but we can kind of enrich the infrastructure state not only with the container name, but with all the information that are related to the Kubernetes objects, essentially. So, for instance, if we're looking at in this example of Nginx, which runs in the cluster name demo cube AWS on that node, on that deployment, we can actually enforce rules on top of these tokens, essentially. So, all the orchestrator metadata are retrieved from Falco with the API calls to the Kubernetes API server, and enrich essentially the internal state that we keep within Falco. Another nice integration that we recently added at the end of last year, when essentially the Kubernetes audit events became GA. Kate's audit or Kubernetes audit events are essentially audit events that are done on the Kubernetes API server. So every time you do an API request to the Kubernetes API server, whether it's through kubectl or classic REST API, you're going to trigger, if you have this feature configured, you're going to trigger the Kubernetes API server to emit in some sort of JSON format an audit event related to that event, related to that action. So for instance, if you delete a pod, you do a kubectl delete, that will trigger the API call for the delete, and the audit event related to that delete will be the user with those credentials, with that token at that particular point in time, on that namespace and on all the related audit information of that event. That will be packed into a JSON and will be sent to, for instance, the webhook, or to a file, or to other streams. But we provide the possibility to configure a webhook that ingests these events as a REST, essentially HTTP webhook. And so we're actually integrated with the Kubernetes audit events very tightly, in the sense that you can configure it and you can write rules on top of it. So essentially the rule grammar has been extended to match this kind of JSON streams. And this is the equivalent of the what I showed before with the delete, just that this is a create. And again, to kind of just to jump back to the purpose here, this is a rule that tries to that detects the creation of a pod in a namespace that is either kube system or kube public. And why is this important? Because generally those namespaces shouldn't onboard new pods. You shouldn't let your developers or your DevOps create pods within that namespaces. As a good practice or as an organization practice, you should create another namespace that hosts all the pods for your service. So if that happens, that might not be necessarily something bad, but you might want to alert your DevOps so that you might go and chase after the person who did that, and try to clean up the thing. So this is again, just to kind of iterate, this is a classic detection use case where Falco can play really nicely. And as I said before, Falco can be seen as a building block. It's an open source CNCF project, and you can think about it as being integrated with the entire ecosystem essentially. So we can output to standard output and let the fluentd collect the logs, propagate it up to the classic EFK stack, so that you have all the things indexed, and then you can create the visualization and dashboards on top of it, as you can see here. So you can very clearly have for the last 15 minutes the 10 topmost triggered rules, and you can print a very nice, but probably not very useful pie chart. Just to give you an example, and this is all in our blog. It's very simple to get started, and by following the examples, you can have a very clear hands-on experience on this kind of tool. Everything is open source with the real purpose of encouraging people to try it out and maybe get creative and use it in their own project, in their own use cases. And that's about it. I try to be very rapid in my talk and try to touch these three components. Clearly, there's for each individual component there might be more to say, but the purpose of this talk was just to be an overview on top of on Falco essentially. So thank you very much for attending and for your attention.